Hello everyone and welcome back to Thermodynamics. We've been spending some time looking at open processes, and in particular, we've recently been looking at how to use the second law for open processes. Now, in doing that, we've introduced the idea of specific entropy. And in today's class, we're going to talk about how we find specific entropy in different cases. So this is the second law rate equation for open systems. We know that to figure out if a system is possible or if a process is possible, we have to look to make sure that the entropy generation rate, sigma dot, is positive. For real processes, we know this is positive. We know we can approach but never equal the ideal case where the entropy generation is zero. And we know if we find that sigma dot is less than zero, the process is not possible. We talked about how to evaluate this heat transfer term, and we've shown a couple of times how to deal with these, finding the amount of entropy that's coming in and out with the mass, but we've never explicitly talked about how to fix S in and S out. How do we find specific internal entropy? It's just like when we're finding specific enthalpy, we need to ask the question, what's the fluid? And if the fluid is something like water, this is pretty straightforward. If we have something like steam or vapor, we look it up in a table and we'll have to do some interpolation and find some interpolation factor. If we're under the vapor dome, we need to be able to find the quality. And if we know the quality, then we can find the specific entropy. If we have a subcooled liquid, things can get a little bit more interesting. So here in the subcooled liquid region, we do have two options. The first is probably not a surprise. You can do a double interpolation. The second is if we're using a process that has an inlet of a subcooled liquid and an outlet of a subcooled liquid, then we can take delta S is equal to Cp, that's the specific heat at constant pressure, times the natural log of T2 over T1. This looks a little bit like delta H is Cp times delta T, except instead of delta T, we have this natural log of the ratio of the temperatures. Again, your spidey sense should be tingling here because neither of these two temperatures is a delta T, so that means we need to use absolute temperatures when we're finding the ratio of those two temperatures. So underneath the vapor dome and as vapors, this is pretty much what we'd expect. But when we're dealing with a process that goes from one subcooled liquid to another subcooled liquid, we have this new equation that looks like something we'd apply when we're assuming that the specific heat is constant. Ideal gases are also a little bit trickier. So there's a couple options here. In fact, we have three different options, and the first involves looking up an answer on table A22 in the textbook. Now the issue is that A22 in the textbook doesn't tell you the specific entropy. It gives you this specific entropy superscript 0. Now you might look at that and wonder what it means. So it turns out that for ideal gases, we can only look up these values. I think it's A22 if it's air, and maybe A23 if it's other ideal gases. Here, we're using this because the change in specific entropy is a function of both temperature and pressure. So we can break this down, and it turns out that the part of the change that's related to pressure is well predicted by this term, which is the specific gas constant. Remember, that's R bar divided by capital M times the natural log of P2 divided by P1. That's if we're calculating S2 minus S1. We would invert this fraction if we had S1 minus S2. But then we have this part of the specific entropy that changes as a function of the temperature. So this S superscript 0 tells us about how the specific entropy changes as the temperature changes. So S superscript 0 captures that change with respect to the temperature. and the part that's captured by the pressure is given by this part of the equation here. You'll notice that this equation is on the equation sheet that we've prepared for this class. Now we have two other options, and they both depend on, first, assuming that the specific heats are constant, and second, which one you pick depends on the information that you've been given. So if we know the change in pressure, which often happens in open systems, we would use this equation. So again, we have the change in the total specific entropy is some function that's got to do with the change in the temperature and the change in the pressure. You'll notice this part looks a little bit like what we saw for subcooled liquids. And then this looks like the same pressure difference part that we saw for ideal gases when we were using the table. Now, if we know the change in specific volume, our equation gets a little bit different. So usually if we're talking about closed systems, like a piston cylinder assembly, we'll often know how the volume or the specific volume changes. So in this case, we still have S2 minus S1. We still have this part here, which is some ratio of the pressures. Notice that this changes from Cp to Cv. And then we have another term. Notice this is plus instead of minus. And now it's the natural log of a ratio of specific volumes instead of a ratio of pressures. So if I knew the pressure difference, again, that usually happens in open systems, then I'll use this option, option 2. But if I know the ratio of the volumes, then I'll use option 3. It's important to remember that methods 2 and 3 here both assume constant specific heat. And that means that especially as our temperature differences get bigger, the accuracy of these two models or these two predictions gets worse. So if you have access to the tables are more accurate. This would sometimes be called an air standard analysis when we're not assuming constant specific heat. So if we have a cold air standard analysis for ideal gases, that means specific heats are constant, and then for delta U we use Cv delta T. For delta H, we use Cp delta T. And then for delta S, we can use either of these two equations that I've introduced here today. So that kind of goes over how we can calculate S or delta S, but I'd like to go over a bit of an example so that you can see it. Now this example you may remember from when we were doing the first law on open systems. This is a heat exchanger. It's a shell and tube heat exchanger, and just like we did for open systems with the first law, we can do this problem many different ways. So we can draw the control volume 3 different ways. We can draw the control volume for the whole heat exchanger. We can do the control volume just the air side or just the refrigerant side. But now, instead of trying to find conservation of mass or conservation of energy, we're asking, is this process possible? When you hear this question, you should immediately think, oh, this is a second law problem, at least possibly, right? So now I can try to figure out if the entropy generation rate is positive, right? So now I have my second law analysis. But the first thing we do before we analyze an open system is say, where are we going to draw the control volume? So first, I will do this problem looking at the whole heat exchanger. Then I'll do just the air side. Then I'll do just the refrigerant side. If I'm doing the whole system, I assume that the process is steady state, that it's adiabatic, so heat transfer is happening between the hot side and the cold side, but there is no heat transfer between the heat exchanger and the surroundings. It's no longer one inlet, one outlet, because now I have an inlet for air and an inlet for refrigerant, and the same on the outlet side. So now I can take my second law and isolate this sigma dot, or entropy generation term. And I see that it's the sum of m dot out S out minus the sum of m dot in S in. Just like I did in the first law, I'm going to collect these terms by the type of mass. So I have m dot air times S2 minus S1, that's the outlet of the air minus the inlet of the air, plus m dot of the refrigerant times the outlet of the refrigerant, S4, multiplied by the inlet, S3. I know for this process to be possible, sigma dot has to be bigger than 0. So again, I have a symbolic solution. I've done this work. I've demonstrated my understanding of thermodynamics by starting with a first principles approach, in this case, writing down the second law, telling you the assumptions. And now I'm going to try to evaluate this analytically. I know the mass flow rate of air. I don't know S2, S1. I do know the mass flow rate of the refrigerant. I don't know S4, and I don't know S3. So I have to be able to fix the states to figure out what's going on. So the refrigerant, you may remember, started as a two-phase mixture at state 3. I know that the temperature here was 15.74 degrees Celsius. And I can see on my TS diagram, now we're drawing this as a TS diagram, I just draw a vertical line down here and I can find the specific entropy. But really I'll fix this on a table, right? So I know for this mixture that's under the vapor dome, S3 is going to be SF plus X times SG minus SF. So it's got to be in between 0.2723 kilojoules per kilogram Kelvin and 0.9117 kilojoules per kilogram Kelvin. You may remember from the last example, you can go back and see, but the quality in this case was 0.2. So I can work this out and I find that the specific entropy at state 3 is 0.4002. So that's good, right? Here's our state table for this problem. We filled this out before, right? The quality was 0.2. Now I can fill in the specific entropy. Now I want to find state 4. I remember this was a saturated vapor. I had the pressure, which is 5 bar, and I had the temperature of 20 degrees. So I'm going to go to the superheated vapor tables for R134A and find S4. Here, I find the table for 5 bar. I have a table here, so I don't have to double interpolate. I have a row of 20 degrees, so I can just read this off, and S4 is 0.9264 kilojoules per kilogram Kelvin. I put that in my state table, and I'm halfway done. So now I'm going to find out, how do I work out delta S for air? So I could do this 2 ways. Well, 3 ways really, because I can assume that it's variable specific heat, and I can look that up on table A22, right? That's that S superscript 0 terms we talked about. I can use the equation for constant specific heat if I know the temperatures and the pressures, and I can use the expression for constant specific heat if I know the temperatures and the specific volumes. So what am I going to do? First, I'm going to find delta S using the tables. So here I know the tables, S2 minus S1 is going to be the change in S superscript 0, right? Notice this is S2 minus S1, so this is S2 superscript 0 minus S2 superscript 1. This tells me how the specific entropy is changing because of the temperature. And then I have this term which is related to the pressure, right? So now I got to look for A22 or A23. In this case, it's air, so I look on A22. Or I can pick one of these 2 expressions if I know the temperatures or the pressures, or if I know the temperatures and the specific volumes, right? B and C require me to assume that specific heat is constant, right? Because these terms are multiplied by specific heat, and I'm not integrating over temperature. In this case, I know T2 and T1, and I know P2 and P1. I still know T2 and T1, but I don't know the specific volumes. So the logical choice, if I was going to assume specific heats, is to use option B on my list. So really now I'm choosing between A and B, and I've kind of eliminated using C. I know also that because A does not require me to assume that the specific heats are constant, A is a more accurate answer, particularly true as my temperature range gets bigger and bigger. So that's what I'll do first. I'll work this problem through both ways, right? So here we can see that S1 minus S2 is equal to S1 superscript 0 minus S2 superscript 0 minus R times ln P2 over P1. So I know the temperature at state 1 is 32 degrees, But here, you can't see the legend up here. These temperatures are not in degrees Celsius, they're in degree Kelvin. So I got to add 273, and I see that I'm at 305. Thankfully, I have a row that's 305 right here on my table. So I can put S1 into my equation. S2 happens at 22 degrees or 295 degrees Kelvin. It's also a row on my table, so I can take that number and plug it into my equation. So now I know S1 superscript 0, S2 superscript 0, and I know these pressures, right? So just remember, when you're looking at this table, this is S superscript 0. This is not S. You can't just take delta S superscript 0 and get the right answer, because your pressures are going to change as well, right? So I have now all the information. I know R, I know P1, and I know P2. So I can put this information into my equation, work this all out. All of these terms are in kilojoules per kilogram Kelvin, so I'm in a good place here. I can see that S1 minus S2 is 0.019 approximately kilojoules per kilogram Kelvin. So now I can put that into my equation here. Notice that when I'm using this equation, even when I'm assuming variable specific heats, I never actually find the specific entropy of state 1 or the specific entropy of state 2. Instead, I only find the difference. But that's okay, because this only asks me for the difference. I do have to notice here that here in this equation, this is S2 minus S1. And what I've calculated down here is S1 minus S2. So I'm probably going to have to multiply this by -1 at some point. But I know m dot air. Now I don't know either S2 or S1, but I know the difference between them. I know m dot r, I know S4, and I know S3. So I'm in pretty good shape here. First, I'm going to evaluate this first term here. I know the mass flow rate. Remember, I had to multiply by -1 because it's S2 minus S1 and not S1 minus S2. And over here, my kilograms cancel, and I'm going to get a negative number here. So this, I'm starting to get a little bit worried, right? Because I know sigma dot has to be positive. And if both of these terms were positive, I would just be able to say right off the bat, hey, don't worry, this is going to be possible. But here, in this case, I get this negative term for m dot air times S2 minus S1. So that means I'm really hoping that on the refrigerant side, I get a positive number that's bigger than this number. And this kind of makes sense, right? Because we're cooling the air down. And remember, when we looked at condensation reactions, when we were cooling things down, we would get that the entropy in that piece of mass would go down. And that's exactly what we see here, right? So now let's evaluate this second term, m dot r times S4 minus S3. So I work this out. It's a positive number, so that's good. I put this in, and I see that this positive number is bigger than this negative number. So when I work it out, I get that sigma dot is 0.0151 kilowatts per degree Kelvin. So it looks like this is possible when I do the whole system, right? So I could just end here, right? But you did have other choices, right? You could have assumed that this was happening at constant specific heat, right? And we could have looked at either the air side or the refrigerant side. So I'll go through this in different ways just to give you some more experience on how to do this, right? So here, I'm going to assume that this is constant specific heat. Here, I've used the subscript FE because the FE handbook, I think, doesn't have the equivalent of table A22 or A23. So if you were doing the FE exam, at least in the year where I looked in the book, you were sort of limited to assuming that this happens at constant specific heat. Again, we know the temperature and pressure at state 1, and we know the temperature and pressure at state 2. So we can put this information into our equation. Here in the first term, right, I get 1 kilojoule per kilogram Kelvin times the natural log of 295 divided by 305. Remember, I got to use Kelvin, right? And I get a negative answer here, just like I got a negative answer when I was doing it in the book, right? So now I can find R times the natural log of P2 divided by P1. I can work this out. This is also a negative answer, right? Because here I'm looking at the air side, and that's what I'm cooling down. So in total, As I'm cooling down the air, I'm decreasing the specific entropy. But this is what I expect because I'm cooling stuff down, right? And here my answer is pretty good, right? Pretty good compared to the answer that I got in the table. It's almost the same because our temperature window here between state 2 and state 1 is pretty narrow. So now I can work out what the second law rate equation looks like if I just look on the air side, right? So here I can assume that delta S or ds by dt goes to 0 because we're at steady state. Now, because I'm only looking at the air side, it's one inlet and one outlet. And I can't get rid of that heat transfer rate term. Personally, I think if I'm going to make a mistake on a question like this is the term I'm most likely to make the mistake on. Because I got to get the sign of the heat transfer right. I got to pick the right temperature. And I have to pick the right unit, right? Because this has to be in absolute temperatures, right? But I can still do the problem this way. But if I got a choice, I'm probably going to use the whole heat exchanger. But I might not always have a choice, right? So I want to show that sigma dot in this control volume on the air side is bigger than 0. I know the heat transfer. I know the temperature of the surroundings, or the temperature outside of my control volume. In this case, we're on the air side, so what's the temperature of the refrigerant? I know the mass flow rate of air, and I know S2 minus S1, because I worked that out already. I worked it out with constant specific heat and with variable specific heat, and I saw that the answers were pretty close to being the same. So now I'm going to work out this second term. I know the mass flow rate. I know really I figured out S1 minus S2, so I'll multiply that by -1, right? The kilograms cancel, and again, I get a negative value here, right? So again, maybe I'm a little bit worried because here I get a negative value, which means that I need this value to be positive and bigger than that value. So let's see what happens when I work out this heat transfer term. So I know that the heat transfer from the air to the refrigerant is negative 9.5 kilowatts. That's the heat transfer rate because the air is cooling down. Heat in is positive, so heat out must be negative. So that gets us through one of the problems of dealing with this particular term, right? But there's other problems too. Namely, we have to figure out which temperature to pick. So T3 is 15.7 degrees, right? That's the temperature. Remember we were under the vapor dome? T4, that's 20 degrees. I can convert both of these to Kelvin. I'm going to do that right away because I know for sure that I need to be able to put these things in absolute temperatures because this is not a delta T situation. This is a temperature that stands alone. So I have to put it into Kelvin. So I'll do that right away so I don't forget. But now, which temperature should I pick? Should I pick T3? Should I pick T4? I think, right? So I want to make sure that this process is possible, right? So I'm going to pick the number that's more conservative. And in this case, when we talk about in engineering, when we talk about picking a conservative number or making a conservative approximation, what we're really talking about is I'm going to pick the number that gets me closer to the answer I don't want to have, right? I'm going to pick the number that's going to tell me that I'm safer than I actually am, right? So here, I'm going to pick this higher temperature value because then this term, which I know is going to be positive because I'm going to have a negative times a negative, right? So I'm going to pick the bigger value in the denominator because that will make this positive term smaller. And if that smaller term is still bigger than this negative number, then I'm going to feel pretty confident that it actually does have a positive entropy generation rate. So now I know which heat transfer I want to pick. I know which temperature I want to pick. I put these both in and I see that I get an entropy generation rate in this first term of 0.0324. And that's great because that's bigger than the entropy generation rate we have in here, which was negative. So when I put these two numbers together, I get that the entropy generation rate on the air side is 0.0146. And I've already seen that it doesn't matter too much in this case if I picked variable specific heats or constant specific heats, I get basically the same number. So if I just look on the air side, I'm still generating entropy. So this looks possible if I do it on the air side, right? So this is bigger than 0, which means that it can actually happen. Now I could also do this problem just on the liquid side. And if I did this problem just on the liquid side, at least the analysis from a symbolic point of view is going to look just like when I did it on the air side. I'm going to say we're steady state, that we're one inlet, one outlet, but I have to keep the heat transfer term because now I know that the refrigerant is accepting heat from the air side. So I got to make sure I get that sign right. But again, I can isolate for my entropy generation rate on the refrigerant side. I have now my heat transfer term and I have my mass flow rate term. I want to show that this is bigger than 0 so that this process is possible. I know the heat coming into the refrigerant side from the air, right? This is the same heat we would calculate from the first law. This is going to be this number, but now this is heat into the refrigerant, so this should be the positive version of this number. I hopefully can figure out the temperature of the surroundings. I'm going to get the mass flow rate of the refrigerant. That's something I have already. I know S4 and S3 because I already evaluated this for the whole system. So hopefully I should be able to do this. First, I'm going to calculate the mass flow rate term, right? I know the mass flow rate and I know S4 and S3. So I evaluate this and I get a positive number. So now I know the contribution to the entropy generation rate that comes about from this mass flow rate term, right? And this is good because it's a positive number and I want to show that sigma dot is positive. The problem is now I got to deal with this heat transfer term. Now the heat transfer term, I got to do two things. So first I got to add a heat transfer rate, and I know that it's positive in this case, which is going to make this term negative because I multiply it by -1. And then I got to pick the right temperature for the surroundings. So here I know that the heat transfer from the perspective of the refrigerant is positive 9.5 kilowatts because the refrigerant is accepting heat from the air. T1 is 305, right? So now we got to pick the right temperature, right? I know it's got to be in Kelvin. So now I'm going to look at my two choices, right? So it's got to be the temperature on the boundary or outside of my control volume. So I have two numbers that I can really pick through here. One is 305 degrees Kelvin and one is 295 Kelvin. So which temperature here should I pick? Just like last time, I want to pick the conservative number, right? But last time, this was a positive value, so I wanted to pick the smaller positive value. I wanted to make that positive value as small as I could. In this case, because I can see that this heat transfer term is going to be negative, so I want to pick the value that's more conservative. I would like for this value to be as large as it can be because it's a negative number. So I'm going to pick T2 here because T2 gives me the smaller denominator, which will give me a larger negative term. So as I work this out, I get negative 9.5 kilowatts divided by 295 Kelvin, which is negative 0.0322 kilowatts per Kelvin. Now this one's pretty close. My negative term is very close to my positive term, but it's smaller. So when I work this out, I do get a small but positive entropy generation rate. So this process looks like it's possible. But if I was really doing this analytically, because anytime we make assumptions, we're always getting a little bit further away from the truth, I might want to actually test this out experimentally just because this value is really, really close or starts to look really close to what would be an ideal heat exchanger, right? So here's my heat. If I looked at the entire heat exchanger, I would look at the entropy generation from the air, the entropy generated from the refrigerant. I'd add them up and I'd get 0.0153 kilowatts per degree Kelvin. And that's pretty close to the total entropy generation rate that I got from the system. So in general, when you're doing a problem like this, my advice would be you need to, well, it's better if you can look at the whole system. Your life will probably be easier because then all you have to do is fix the states. If you're going to make a mistake, at least in my experience, it's going to happen in that heat transfer term. But it might be that on the exam, ask a question and sort of force you to demonstrate that you understand how to use that heat transfer term. So the other thing I guess that we want to say here is that when we're doing these types of second law problems, there's different ways that we can fix the specific entropy. And some of them are the same as the way we'd fix something like specific enthalpy, particularly if we're dealing with water that's under the vapor dome or that's a superheated vapor. But if we're dealing with liquids, something that goes from a liquid to a liquid, or if we're dealing with an ideal gas, then there are other ways to fix the state. If it's an ideal gas, we got to ask, is it constant specific heat or variable specific heat? If it's variable specific heat, I got to remember that at S superscript 0 is not the same thing as S. There's other things to do for that equation. And if it's constant specific heat, I've got to see if I know the temperatures and the pressures, or if I know the temperatures and the specific volumes. So that's all that I have for you today, and I look forward to seeing you next time on Virtual Thermodynamics.